This is number 35 from chapter 10. The question is asking us to determine the electronic geometry, molecular geometry, and idealized bond angles for each molecule. In which cases do you expect deviations from the idealized bond angle? So we have four different molecules that we have to put together. So A is looking at PF3, and so if we put that structure together, we would end up with something that looks like this. This would have an electronic geometry that would be tetrahedral. Its molecular structure, though, would be trigonal pyramidal. We would expect angles of 109.5 degrees for this type of electronic tetrahedral arrangement, but because of the lone pair, there will be deviations from that electronic idealized angle of 109.5. So that's part A, and we're going to do the same type of process for the rest. Part B looks at sulfur dibromide here, SBr2. And if we put that structure together, we get a molecule that looks like this. And our electronic geometry here again would still be tetrahedral. Just like with part A, we have four groups surrounding that central element, in this case sulfur. But our molecular geometry would be bent when we take those lone pairs kind of out of the picture. We would still expect angles of 109.5 because of that tetrahedral electronic geometry, but because of now the two lone pairs, we would still see deviations. Remember, the more lone pairs that we have, the more of a deviation we're going to see because lone pair forces of repulsion there, because they're electrons, is greater than bonding pairs and their repulsive forces. So that's part A and part B. Part C looks at a molecule known as chloroform, or CH-Cl3. Here we have three chlorines and a hydrogen surrounding that central carbon element. And we have an electronic geometry which would be a tetrahedral, again because of those four groups. And in this case, the molecular geometry and the electronic geometry are the same. Both are tetrahedral. And we would expect 109.5 degrees, again, for the bond angles. And this is actually going to be very, very, very close to 109.5. But because there are electronegativity differences with the chlorines and the hydrogen, we will see very, very small deviations as a result, since we don't have a perfect symmetry about the central carbon atom. Part D looks at CS2, or carbon disulfide. This looks very much the same as carbon dioxide, where we have carbon with two double bonds to each sulfur. Our electronic geometry is going to be linear, and again we see the same with our molecular in this case. So we used to have linear geometry both in the electronic as well as the molecular. And the angle we would see here is 180 degrees. Since we have the same elements surrounding the carbons, we would not expect any deviation, not even one that is small. So we would have no deviations for carbon disulfide. That is number 35.